So at this point, to really understand the metric of resolution, which we just introduced, we need to understand what the origin of the peak shape is. Why does it look the way it does? We call that type of shape a Gaussian type shape, which I mentioned briefly in the previous video. But what causes that? Well, this is a physical and chemical phenomenon, but primarily a physical one that's defined by Fick's laws of diffusion. So imagine this is Fick's law. What Fick's law tells us is that if you have a, um, a concentration gradient, it could be chemicals, it could be anything. If you have a higher local density of something and a lower local density away from that, you will have a flux away from that source, which is going to be equal to minus d, d being the diffusion coefficient that we're used to, dc dx, dc being the change in concentration, dx being the change in distance. So this is a 1D system. So when you think about a generic column like we have here. Let me make this a little bit bigger. If we have a generic column, oops, imagine you have an injection where you inject your sample right here, right, at time 0, at distance 0. So this is x equals 0, time equals 0. And let's hypothesize that you can inject that in an infinitely thin sliver, meaning you've got an infinitely small amount of your sample, right? Because you imagine if you've got a syringe, a big old syringe, and you inject like several milliliters onto your column, it's not going to look like a nice thin band. It's going to smear out because you've got tons of your sample on there. So if you have a tiny, tiny, tiny bit of sample, imagine now, though, that as this thing starts to move in this dimension along the column, this is a concentration gradient where you have a locally high concentration right in the center of this band where you've injected all of your sample. And there's going to be a driving force for diffusion in both directions, not just in the direction of the flow. This is the flow direction across the stationary column. With the mobile phase, it doesn't matter. This thing doesn't see flow, it simply sees concentration gradient and then is going to diffuse outwardly in a dimension like this. And what we see at this moment in time, if we were to extract a sort of two-dimensional profile, would be the start of a Gaussian distribution. As this thing spends more time on the column or moves a further distance, both of those being equated to each other, then we get a wider band, which we call band broadening. And so this is the diffusion contribution that's unavoidable. There are things, of course, that we can do to minimize this effect, which we'll talk about. But this is a fact of life when it comes to trying to separate a high concentration of a substance over a long distance, right? We're going to end up with a greater broadening, which means what for our resolution? Well, remember, our resolution is the capacity to separate two things. But as two things start to broaden into each other, then you have sort of an opposing force, right? You know that the longer your compound spends on the column, the more separation you'll get between two different compounds simply because there's more equilibrium events. There's more access that your compounds have to the stationary phase, which means that over time those things will move further apart. The retention time difference will grow further apart. But at the same time, the full width at half max or the width at their base also grows. And so those two things are sort of working inverse to each other when it comes to separation. There's tricks, which we'll talk about, which give rise to different things that we do in chromatography and actually different techniques in chromatography in general. So one thing we can do to actually extract this concentration profile as a function of x or distance would be to integrate the Fick's law equation. So what we get is this expression for concentration, or C, as a function of x here, but also as a function of our constant, our diffusion coefficient here. If you look at this may not strike you as interesting at first, but if you look at this, it bears enormous resemblance to an equation that you saw in chapter 4, which was in statistics. And this is the equation that we call for the normal distribution, or the Gaussian distribution. So this is the generic representation of the normal distribution that we talked so much about in chapter 4. They're identical, and that's what gives rise to the shape of a curve if we're only considering diffusion here. Of course, there's more effects that we'll consider later, but if we simply consider diffusion in a Gaussian type way, it turns out to be the same sort of profile, which allows us then to take the standard deviation of this distribution. And remember, the standard deviation, just like in the normal distribution that we talked about in chapter 4, really is just a metric for the width. And so the standard deviation here is really just a metric for the width of a band. And so that is sigma in this case. And sigma, if we're taking the standard deviation of the concentration profile as a Gaussian type distribution, sigma is equal to root 2 dt. So this tells us, many things, but the first thing it tells us is that the width or the broadening effect is roughly, or not roughly, it's proportional to the square root of time, because 2 and d are constants. And so that is the first sort of conclusion that we get here, time being how long is our compound on the column, right? Because if you have a concentration gradient, then the longer that thing is allowed to diffuse or flux away from that concentration gradient, it will. And so this points us to, faster separations might be better if we want to minimize the band broadening simply based on the square root of the time that we're proceeding with the separation. So this solution here, this standard deviation, is the same standard deviation for what we call the one-dimensional random walk equation. So one-dimensional random walk is used in all sorts of fields, not just chemistry and not just chemical separations, though we use it in many different areas in chemistry. The 1D random walk, although I won't derive it, is based on the binomial distribution where you sort of hypothetically have an axis, this is our 1D axis, with different positions x along the way. So these are all just discrete positions, and what we could do is go through here at several different time points, time 1, time 2, time 3, and you essentially hypothesize if you have a person here and they start at time 0 and then move to time 1, and they have options to either move to the left to position -1 or to the right to position 1, then well, at least at time 1, we'll say that the probability of existing in position 1 is 1. But then at time 2, after they've made this transition, then the probability of existing at this position 0 is going to be 0, and they will have a 50% chance, or 1/2 times probability of existing at -1 and 1/2 existing at +1, and this sort of spiders out from here. As the person is in either -1 position or 1 position, then they have a 50% chance of going back and forth. And what you end up is, if you simulate this out to t approaches infinity, is you end up with this distribution that looks exactly like this. And so this is really just a solution to the one-dimensional fixed law, which is a binomial distribution, simply based on the randomness of a particle, in this case not a person, being able to move in dimension A or dimension B, in either forward or backward. Of course, this gets translated into 3 dimensions, and so there are solutions to the 3-dimensional fixed law. So it's the 3-dimensional random walk equation that is more directly relevant to diffusion in a column, but it's also the sort of best descriptor for how gases diffuse from high concentration to low. And so what I have here is a MATLAB simulation that I just grabbed off YouTube of the 3-dimensional random walk, which is, you could imagine as being just a particle in space, or you could imagine it being a particle inside of a column where it has this sort of randomized binomial decision choice to move in x, y, and z dimensions at any given moment in time. So it looks like this. You can just see the particle moving. This is 2 times playback speed, so this is moving pretty quickly. But this is a binomial distribution then in 3 dimensions. Of course, these points are discretized, so the distance moved is finite in the constant at each point, which gives it this sort of geometric looking shape. But many things in the physical world behave in this sort of random walk or binomial distribution. So one thing that's handy about the random walk equation here is that we could, time is helpful, but in terms of chromatography, it's helpful to think about the finite length of the column and how band broadening is going to be impacted over the actual length that a molecule or a band of molecules will move. And so we can do that by just thinking about how fast that particle is moving in one dimension. Again, we're only solving things in one dimension here, which we call the linear velocity of the solute, solute of this thing. So we call that ux, and that's simply just going to be distance over time, as you'd imagine. What we can do is then just rearrange this for time. And so if we rearrange this for time, we get time is equal to x over the linear velocity. Now we can take that time and we can substitute it in here, although we're not going to use sigma, we're actually going to use sigma squared. So sigma squared, if you think back to chapter 4, the square of the standard deviation is this thing called the variance, which is again just another proxy for the band broadening of the system. So if we take that and we substitute it, that's going to give us 2 times d times t. In this case, that's going to be x over ux. So that's where we are right now. So I didn't solve anything differently, but in green here I just collected the 2d over ux and just put that in brackets and then pulled the x out. And so what this really quick substitution allows us to do is think about the broadening, which the variance of the band is a proxy for. It's just the standard deviation squared of this band. The relationship between that and the distance traveled, x. And what you see here is that they're related linearly through this constant of proportionality, which is 2 times the diffusion constant divided by the velocity, the linear velocity in x. So what does that mean? Well, in certain fields this has different meanings, but in terms of separation, as we think about how bands broaden out as they move along the path of separation x here, in separations we call this constant of proportionality the theoretical plate height, and it gets this letter h to signify it, so we call it the theoretical plate height. And it has, as I'll mention, it's really a hypothetical value. It's not necessarily empirical or real thing, but it allows us to quantitatively compare the efficiency or the separating power of a particular chromatography system or a column on a chromatography system using this theoretical plate height. So the plate height, or the theoretical plate height, then I just have this, just grab this out of your textbook, is approximately the length of column. This is hypothetical. Approximately the length of the column required for one equilibration of the solute between the mobile and stationary phases. This approximation comes from the fact that that's the variance, so it's roughly 1 standard deviation squared. So that's why it's approximate and not exactly. And so what that really means is if you have a column, which I have represented by this sort of open tube here, so just this cross section of a column, the h here, the height, the theoretical plate height, is really sort of this imagination or imaginative process where you say, okay, what is the physical distance or height that it takes for my analyte, my compound, and so h is specific to individual compound, it's not generic. So for that particular compound, the height, the plate height, is that physical distance, or approximately that distance that it takes for that compound to go through one equilibration cycle between the mobile phase and the stationary phase. So what that means is if you have this particle and we're computing the theoretical plate height for this particle, as it moves into this space, this height here, and it reaches that first part, that that particle then is going to come down here and it's going to bind with the stationary phase and reach equilibrium. And in doing so, in reaching equilibrium, some amount of it is then going to be released from the system. And that process is occurring because the mobile phase is moving this along the duration, or the distance x of the column. So the height here is literally that distance for one equilibration cycle to occur. How far instead of how long it takes for your particular analyte to reach equilibrium. And so you can imagine that height is a constant for that system if no variables change. And so you can sort of subdivide your entire column into these hypothetical equilibration cycles where your compound keeps going through and then it interacts and doesn't, and interacts and reaches equilibrium. And every time it reaches equilibrium, it starts to separate further and further from, say, another molecule that is doing the same thing as its equilibrating, but maybe that distance is different for that compound, and so it's cycling faster and faster and faster compared with your other. And so it's really just a proxy for how good is your column for your analyte. Of course, if you have more, the more theoretical plates you have over the length of the column, you have more equilibration cycles, which means you're allowing your molecule to interact in the way that the chromatography system was designed to do. So more interactions means more resolving power, means a better capacity to separate two species on your column. So we're always aspiring for a higher number of theoretical plates on it. So then, of course, the number of theoretical plates on a given column is just going to be the length of the column divided by the plate height. So if the length of the column here is L, and this is a finite thing we can measure, maybe our column on our LC is 10 centimeters, then 10 centimeters divided by this sort of hypothetical length for one equilibration cycle for that particular compound under those conditions. It's really important to note that the plate heights are computed per species that you're separating and for any different change in the system parameters. So if you change the flow rate, if you change the volume of injection, if you change the mobile phase, if you change the column width or the column density or the packing density, all of those things would perturb H in this case, or the equilibration length, which would then of course change N. L is going to be fixed for any column that you have. Really, that's just a tube that you buy and then you fill it up with whatever your stationary phase and you run it. And so it's important to know that theoretical plate height and number of theoretical plates isn't some universal value that when you go buy a column it's just fixed, because it's not. It's dependent. And I'll show you how we use chromatograms to extract values for these sort of hypothetical plates. So of course the number of plates, N here, is really just a proxy for the distribution, the broadening of any band, and that band is going to be, as I mentioned many times, a function of any experimental parameters, conditions in your system, but also the analyte itself. And so when you have a chromatogram, the chromatogram may have multiple peaks here like this. You would be computing an N for each one of these particular analytes or compounds or species. Hopefully that makes sense. And from a chromatogram, the empirical methodology to do that, which we're not going to derive because it's beyond the scope and requires us to do a little bit of calculus, but to use an empirical chromatogram like what we have here, then we're going to use the key metrics that we've already used before, our retention time and the full width to half max. And so we're simply just going to take the peak and we're going to measure the full width at half max here, and we're going to measure its retention time here, and we'll be able to extract the theoretical number of plates for this particular species. So you'll do this in a workshop. It's a really nice thing, but it allows you to essentially compute how many times this analyte went through an equilibration cycle on your particular column. This is super powerful. So resolution is this sort of immediate thing, like can I separate, can I resolve two species? Theoretical plate number is really telling you, well, how good is your system? Are you going through 100 cycles or are you going through 50,000 cycles, right? And so that's this sort of more, it's sort of more abstract, but it's really powerful, and that allows us to compute and really think about how well is your analyte interacting with the system to affect a separation from other species. Okay, so that brings us to the question of how is resolution and theoretical plate height actually related to each other. And so I have this expression, which is it's a theoretical expression. It's never really used to compute resolution, because resolution it's this empirical parameter. It is whatever you actually extracted, but it is a useful functional relationship which helps us understand the more functional relationships between this parameter resolution, which is empirical, the theoretical number of plates, which is mostly theoretical value, and some other parameters. So in the equation here, of course, resolution, this is all equal to resolution, and big N here is the theoretical number of plates on the column. Alpha here is a ratio, and it's a ratio of the retention times between compound 1 and compound 2, because you're computing resolution. So of course you're thinking about two things here that are coming off your column. That's what alpha is. And then K is that retention factor, which I mentioned in the first video, K, which is the sort of relationship between T R over TM, TM being your mobile phase. So that time when your mobile phase first comes off versus TR1 and TR2 here. So, and K2 specifically is for the slower of the peaks, the one that it takes longer to get off of. So when K2 is computed, it's being computed for the second peak of the two that you're comparing. So anyway, none of that really matters that much, because what I want to think about is the implicit sort of functional relationship between resolution and the number of plates. So you've got this very empirical parameter that you measure directly off of off of your chromatogram, and then N, which is related to this very fundamental random walk equation. So here you can see that if you want to increase your resolution, right? Maybe you've got two peaks and they look more like this. You see this and you're like, that's not good enough for me to develop a method to quantitate whatever this compound is. Say you're developing your own method of analysis, which is what analytical chemists do, especially in terms of a wet chemical analysis. So you're saying, okay, I'm developing this technique. Here are these compounds. I'm trying to measure, PFAS in I don't know, cornflakes. And I'm trying to separate these things, and these two compounds are just not resolving well. How should I think about my plate height and my resolution? Well, if I want to think about that, resolution is going to be proportional to the square root of the number of plates, which, if we think about what the number of plates are here, that means it's going to be proportional to the square root of the length of the column divided by the plate height. And so if we want to increase the resolution of our separation, one thing we could do is crank up the length that we're separating this thing over, right? So if we increase our length of our original column by a factor of 4, that should in principle double what our resolution is. If we increase it by a factor of 16, then we should get a 4-fold increase, etc. There's sort of diminishing returns here, because to affect an 8-fold return, you'd have to increase the length of your column by a factor of 64, which becomes impractical in most geometries. And so this is a nice way to really think about the relationship between resolution and these sort of more fundamental parameters. Of course, the plate height is something that requires a little bit more thought. Length is easy, right? We can just change that simply and then impact the resolution directly in a root sort of functional form here. Plate height, though, that is based on the chemistry, both of your analyte and the stationary phase. So to impact that, you know, to decrease that plate height, which would increase the number of plates, which would then also increase the resolution, we would have to fine-tune our chemistry a little bit. Or another thing we can do is change, say, like the particle size. So if your column is packed with a whole bunch of beads here, if you, as you imagine, if you decrease the size of those beads from millimeter to micrometer to, you know, infinitely small in the nanometer range, then you end up having a ton of potential sites where your compound can interact with. And so you can decrease your plate height because your molecule doesn't have to move very far because there's way more surface area exposed with that particular chemistry. So that's another mechanism. As you can imagine, you can think about things hypothetically like that, but then almost immediately you run into practical constraints, because if you make really, really tiny particles and you pack this thing in, then there's no chance that you're going to get liquid through it because of the capillary forces of water, especially. So anything that that has a fairly high capillary force like water is not going to be pushed through really, really tiny beads unless you crank up the pressure, which, as you can imagine, is the origin of high pressure liquid chromatography. Because if we shrink down our particle size smaller and smaller, we can decrease our plate height, which decreases the number of plates on the column, which then increases our resolving power, our separation efficiency. And as I mentioned in a previous video at CC, we have this thing called a UHPLC, ultra high pressure, which means that we go to much higher pressures in the tens of thousands of PSI in order to force mobile phase through very tiny particles. What that allows us to do is a couple things. One, we can have really small particles and still get liquid through it, but we can sort of compensate where we use smaller particles, which allows us to use a shorter length column at the same time. You know, we would do better if we had a longer length and the sort of shorter theoretical plates. But as you can imagine, time is also working against us, because the longer we allow our concentrated band to sit on the column, if this is your band of stuff, the longer we allow that, which is a function of its length of the column, the more the diffusion is going to increase and the broader this thing is going to get. And so with ultra high performance or pressure liquid chromatography, you shorten the column, which means you can do separations on the order of like a minute, really short, while still maximizing your equilibration between your analyte and the stationary phase by having really, really tiny particles. And so this equation, which is the Purnell equation, really helps you start to rationalize the hypothetical changes that you could make to a system and then weigh that against the practical. So you're not going to need to necessarily use this to compute resolution for anything, so don't worry about alpha and K2, because I don't really care that you can compute resolution in this form. What I really want you to be able to understand is conceptually the relationship between these key parameters and how you would maybe increase the separation efficiency of some hypothetical separation based on a variety of different parameters.